scalar multiplication. For this, let's look at what happens if we were to take some vector and multiply it by a scalar. So let's say we have k times vector a. When multiplying a vector by a scalar, it might get longer or shorter depending on the value of k, but the result will always be a vector that's parallel to the original vector, either in the same direction or the exact opposite direction. If k is bigger than 0, then k times vector a is going to be in the same direction as vector a, and with a magnitude equal to k times the magnitude of a. But if k is less than 0, so if it's negative, k times vector a is in the opposite direction as vector a, and its magnitude is equal to the absolute value of k times the magnitude of a. And the best way for me to clarify what this all means to you is with an example. So let's say we have some vector, vector u, that is pointed straight up to the north, and its magnitude is 10 kilometers an hour. Let's draw what negative vector u, a half times vector u, and negative a half times vector u look like. So let me start by drawing vector u. If I want to draw a negative vector u, that meets the criteria of the scalar being less than 0. Our scalar multiple this time is negative 1. So negative u is going to be in the opposite direction as vector u. And its magnitude is equal to the absolute value of k, well the absolute value of negative 1 is 1, times the magnitude of a. So its magnitude is just being multiplied by 1, so the magnitude is not changing, but it will be going in the opposite direction. So this is the negative of vector u. It's 10 kilometers an hour south. A half times vector u, well that has a positive scalar, so it's going to be in the same direction, and its magnitude is going to be a half times the magnitude of the original vector, which means instead of 10 kilometers an hour north, it's going to be 5 kilometers an hour north. So I need to draw a vector that is half as long, but pointing in the same direction. And lastly, negative a half u is going to just be the exact opposite of a half u. So it's going to have the same magnitude as a half u, but in the opposite direction, which means it's going to be going 5 kilometers an hour south. So hopefully you can see how scalar multiplication works. Let me show you algebraically how we can do it as well. So let's look over at this Cartesian grid. Now let's say we're given vector a in component form is the vector 2, 3. Let's determine what 2 times vector a is. Algebraically, this calculation is quite easy. 2 times vector a would just be 2 times the vector 2, 3. And to do that calculation algebraically, we just have to multiply both of the components of the vector by the scalar that's in front of the vector. So this would equal, I multiply the x component by 2, which is 4, and I also multiply the y component by 2, which is 6. And now let me show you on this Cartesian grid how vector a and 2 times vector a compare to each other. So if I were to draw vector a, I'll start its tail at the origin and put the tip at the point 2, 3. And drawing 2 times vector a, its tail is at the origin and the tip is at the point 4, 6. Notice both vectors are going in the same direction. That's because the scalar is positive. And 2 times vector a is double the length of vector a. Now, one useful application of scalar multiplication of a vector is creating something called a unit vector. So I could create unit vector a, and I could communicate that by putting this little hat above a. That means unit vector a, which means a vector that goes in the exact same direction as a, but it only has a magnitude of 1 unit. So how could we shrink this vector so its magnitude is only 1 unit? Well, we just have to multiply that vector by 1 over its own magnitude. And if I want the magnitude of a, I know it would be equal to the square root of the x component squared plus the y component squared. So 2 squared plus 3 squared is 13. So the magnitude is the square root of 13. If I multiply that by vector a, what this scalar does to this vector is it shrinks its magnitude down to a magnitude of 1, but it keeps it going in the same direction. If I were to multiply both of these components by 1 over root 13, the approximate values of that are 0.55 and 0.83. If I were to draw that vector, let me zoom in, it would be this vector right here. It's in the same direction as a, but its length is only 1 unit.